somewhere in a Chinese testing lab, a battery just did something engineers have spent decades insisting was impossible. Not in theory, not in a simulation, in a real production car on a real road right now. The number is 1,093 kilowatts. That's the peak charging power one company just confirmed their battery can handle. Fast enough to put more range into your car in the time it takes to read this sentence than most EVs get in 20 minutes on a standard fast charger. And the company behind it isn't some hype-chasing startup with a flashy concept car and no factory. It's Geely, one of the two giants currently at war over the future of the electric vehicle industry in China. The other giant is BYD. And what's happening between these two companies right now is going to decide what battery sits under your next car, whether you ever notice it or not. Here's what makes this specific number so strange. For years, every serious battery engineer on the planet believed in something close to an unbreakable law, a rule so consistent across the entire industry that nobody bothered fighting it anymore. Geely just claimed they broke it, and they didn't need some exotic, unproven chemistry to do it. They used the same basic battery type that's already sitting in millions of cars on the road today. To understand why this matters, you need to understand what battery engineers call the impossible triangle. Picture everything you'd actually want from an EV battery. You want it to charge fast, so you're not standing at a charger burning half your afternoon. You want it to last for years without losing its ability to hold a charge. And you want it to be safe, even in a genuinely bad situation. Speed, longevity, safety. Three simple things. The problem is, for as long as batteries have existed, engineers have treated these three goals as a trade-off. Pick any two, and the third one suffers. It wasn't a marketing limitation, it was physics. Push a huge amount of electricity into a battery quickly, and you generate heat. And heat is corrosive to the delicate chemistry inside a cell. Charge fast enough, often enough, and you're quietly destroying the battery's lifespan one session at a time. So if you want a battery to last, the traditional answer has been to slow the charging down and be gentle with it, which means longer waits every time you plug in. And if you want maximum safety, you typically add protective layers and heavier materials between cells, which adds weight and eats into the space you could otherwise use to store energy. Push hard on one corner of the triangle, and the other two corners quietly pay for it. That's been the accepted reality of battery engineering for as long as EVs have existed. And that's exactly what makes Geely claims so disruptive, because they say they didn't sacrifice a single corner. They're using lithium iron phosphate, LFP for short, the same workhorse chemistry that's known across the industry for being safe, durable, and affordable, but never for being fast. And they're claiming it now does all three things at once. This battery is called the Golden Brick, and it's not sitting in a lab. It's already installed in a production sedan on sale in China right now. To appreciate what Geely actually claiming here, you need one more piece of context, because China just rewrote the rulebook on battery safety. And Geely didn't wait for the deadline. A new national standard, GB 38031-2025, takes effect on July 1st, 2026. Under the old rules, a battery only had to warn the driver about 5 minutes before catching fire, enough time to pull over and get out, but the car would still burn. The new standard throws that logic out entirely. Now, a battery has to produce 0 flames and 0 explosions for a full 2 hours after a thermal runaway event begins. There's a new underbody impact test simulating road debris strikes, and LFP battery temperature is now capped at 65 degrees Celsius during charging. Full stop. Geely didn't wait around for the deadline to force their hand. They certified their entire battery lineup against the new standard by May of 2025. Well over a year early, entirely voluntarily. And it's against that backdrop, holding themselves to rules stricter than anywhere else in the world, that they released a battery claiming to conquer all 3 corners of the triangle at once. Let's start with the corner that grabs headlines first: speed. The peak figure is 1,093 kilowatts. On its own, that's just a big number. What actually makes it meaningful is something called the C rate, a way of measuring charging speed relative to a battery's total size. A battery with a C rate of 1 can go from empty to full in about an hour. A C rate of 2 cuts, that to 30 minutes. Aegis Golden Brick hits a C rate of 12. That means, in theory, the entire battery can fill from empty in around 5 minutes. For an LFP battery, that number would have been laughed out of the room a few years ago. But here's the part that actually matters more than the raw speed. What didn't happen while that charge was taking place? When you force electricity into a battery at extreme rates, the heat generated doesn't rise in a straight line. It compounds. Double the current running through a conductor, and the heat doesn't just double, it roughly quadruples. It's the same reason a phone charger cable gets warm on fast charge and can eventually fail if you push it too hard, just at a scale that could genuinely damage a car battery pack. And there's a well-known rule in battery engineering that makes this even more serious. For roughly every 10-degree rise above the ideal operating temperature, the rate of battery degradation doubles. So a small spike in heat during fast charging isn't a minor inconvenience. It's actively shortening the life of the battery in real time. China's new safety law caps LFP charging temperature at 65 degrees. During the 1093 kilowatt test, Aegis battery reportedly held at 64 degrees, 1 single degree under the legal ceiling, while absorbing over a megawatt of power. That's not a small engineering feat. That's razor-close thermal control under extreme load. Aegis says they pulled it off through 3 layers of defense working together. The first is physical cooling design. Most production EVs today cool their battery cells from a single side, a cooling plate pressed against the top or bottom of the cell. Aegis wrapped liquid cooling around both sides of every individual cell, doubling the surface area available to pull heat out and cutting the distance that heat has to travel to escape. The result, according to Aegis, is a 35% improvement in cooling efficiency. Think of the difference between resting a hot pan on a block of ice versus dropping the whole pan into a bucket of ice water. One cools from a single surface, the other cools everywhere at once. The second layer is software. Sensors throughout the pack monitor every individual cell dozens of times per second, not just reading current temperature, but predicting where a heat spike is about to happen before it actually occurs, and redirecting cooling flow to that spot preemptively. Each cell is also wrapped in an aerospace-grade insulating barrier designed to stop heat from one cell from spreading into its neighbors. The third layer attacks the problem at its source instead of reacting to it. Aegis restructured the internal architecture of the cells themselves using a principle called Bernardi's energy balance to physically generate less heat from electrical resistance in the first place. Instead of fighting a fire after it starts, they engineered the cell so there's less fuel for the fire to begin with. All of that is backed by a 900-volt electrical architecture in the vehicle itself versus the 400-volt systems most older EVs still run. Higher voltage works like a wider pipe. The same amount of power can move through with less pressure, and less pressure means less heat. On the road, Aegis says the result is a charge from 10% to 70% in 4 minutes and 22 seconds, and up to 97% in 8 minutes and 42 seconds. Something in the neighborhood of 2 kilometers of range recovered for every second the car sits plugged in. That's enough range for most people's entire day, added in less time than it takes to order a coffee, which raises the obvious question. Charge a battery that aggressively day after day, and doesn't it just fall apart? That's the second corner of the triangle, lifespan. And it's usually where fast charging claims quietly fall apart, because everybody already knows what happens to a phone battery that gets fast charged every single day for a few years. Aegis claims the Golden Brick is rated for 4,500 full charge cycles. One full charge from empty and back down again counts as one cycle. Run the math using a rough real-world figure of 220 kilometers of range per cycle, and 4,500 cycles works out to roughly 990,000 kilometers. Aegis rounds that up and calls it a 1,000,000-kilometer battery. Put simply, most drivers will never come close to putting that many kilometers on a car in their lifetime. The car would fall apart from ordinary wear long before the battery gave out. The obvious question is how you protect a battery from 1,000,000 kilometers of abuse while simultaneously slamming over a megawatt of power into it repeatedly. Aegis points to 2 specific mechanisms. The first deals with physical swelling. When electricity rushes into a cell quickly, the internal materials physically expand, similar to a sponge soaking up water. And if that expansion happens too aggressively or too often, it can crack the internal structure and permanently damage the battery's ability to hold a charge. Geely built 3 technologies to manage that stress together. A self-healing film coats the internal surfaces and conceal microcracks as they form, before they spread. A gel buffer layer gives the internal components room to physically expand and contract without cracking, absorbing the mechanical stress instead of transferring it to rigid materials. And specially engineered binders act like flexible glue, keeping everything bonded together through thousands of expansion cycles. The second mechanism is a protective coating applied directly to the electrodes, designed to shield them from the repeated chemical stress that ultra-fast charging creates, functioning essentially as a barrier that slows down the wear those extreme charge rates would otherwise cause. Without it, the electrodes would likely degrade far faster under 12C charging conditions. Together, Geely says these systems let the battery swell and shrink through all 4,500 cycles without sustaining lasting damage. The electrical equivalent of a running shoe built to survive a marathon every single day for years without the sole falling apart. Speed? Checked. Lifespan? Checked. Which leaves the corner that matters most if something actually goes wrong. This is where Geely's approach gets genuinely extreme, because in a country that just wrote the strictest EV battery safety law in the world, Geely didn't just aim to meet the new standard, they tried to blow past it. Since 2024, Geely says they've run 48 separate testing programs, logging more than 48,000 hours of destructive testing and destroying nearly 7,000 individual samples in the process. Cells and full battery packs sacrificed specifically to find the exact point where things break. Of those 48 protocols, 23 reportedly go beyond what China's new national standard requires, and 12 were tests Geely invented themselves, tests nobody asked them to run. The philosophy behind that obsessive level of testing traces back to something called Heinrich's Law, a principle originally drawn from decades of workplace accident data, which found that for every one catastrophic failure, there are roughly 29 smaller incidents and around 300 near misses that came before it. The logic is simple. Hunt down and eliminate the 300 near misses, and the catastrophe never has a chance to happen. Geely applied that exact thinking to battery engineering, deliberately hunting for weaknesses under extreme lab conditions, so those weaknesses never show up as an emergency on an actual road. Some of the individual tests sound less like quality control and more like a dare. In one, a 36-ton tank is driven directly over a fully assembled battery pack, applying nearly double the force China's national standard requires, and the pack reportedly holds together with no structural failure. In another, Geely fires a 5.56mm round, the same caliber used in a military assault rifle, directly through a fully charged cell at roughly 920 meters per second. The bullet passes clean through. Voltage reportedly stays above 3.2 volts, and nothing ignites. In a third test, designed to simulate the worst possible internal short circuit, multiple 5mm steel needles are driven into a fully charged cell from different angles simultaneously, and the battery is then observed for a full hour afterward. No smoke, no flame, no explosion. It just sits there. Geely's involvement in battery safety apparently extends past their own product line too. They reportedly helped write the new underbody impact test that became part of China's national standard and released a dozen patents related to battery floor safety for the entire industry to use, competitors included. And when it comes to the new 2-hour zero flame requirement specifically, Geely's answer is containment. The same insulating barriers and gel layers used for thermal management are designed so that if one single cell fails, the heat stays locked to that cell. The neighboring cells never even register that something went wrong. The fire doesn't get contained. It never starts in the first place. Speed, lifespan, safety. All 3 corners supposedly checked off at once, but having a remarkable battery is only half of this story, because the other giant in this fight, BYD, already has a battery with a legendary reputation of its own. So does Geely's new battery actually beat BYD's Blade battery? The honest answer is, it depends what you're measuring. Start with infrastructure, because that's where the real gap shows up. The best battery in the world is worthless if there's nowhere to plug it in. BYD has spent years building out its own proprietary flash charging network, and they're already rolling out 1.5 megawatt chargers across Europe this year. BYD controls the entire experience end to end: the car, the charger, the station. Which means when a driver pulls up to a BYD station, it's built specifically to work with their own vehicle. Geely's position is different. Their megawatt charging currently relies on a partner network still in early pilot stages, with stations concentrated in only a handful of cities. To bridge that gap, Geely has struck a deal, giving their drivers access to a much larger existing charging network across China. A smart workaround, but not the same thing as owning the infrastructure outright. Now look at raw peak numbers. BYD's system reportedly tops out at 1,500 kilowatts, higher than Daili's 1,093. On a spec sheet, BYD wins that number outright. But peak lab power isn't what a driver actually experiences on a real trip. What matters is how quickly you go from a low battery to enough range to keep moving. And on that measure, Geely, real-world 10% to 70% and 10% to 97% charge times reportedly edge ahead of BYD's, even with a lower peak number on paper. So there's no clean single winner here. If the question is pure cell-level engineering, has anyone actually built an LFP battery that hits real speed, real longevity, and real safety all at once? Geely appears to have pulled off something the industry spent years calling impossible. That's a legitimate engineering achievement. But if the question is, which company can actually get that battery charged reliably anywhere you drive, BYD's mature self-owned charging network is still the safer bet for now. Having the best battery on the planet means little if you can't find anywhere to plug it in. The question nobody's asking. Yet here's the part of this story worth sitting with. If a well-understood, comparatively affordable chemistry like LFP can already deliver this level of speed, longevity, and safety at once, it raises a real question about why the industry is still pouring billions of dollars into solid-state battery research, technology whose entire promise was solving these exact three problems simultaneously. Geely may have just gotten there first with a chemistry that's been sitting in the industry's toolbox for years. For now, the impossible triangle looks a lot less impossible than it did a year ago, and the rivalry between Geely and BYD is only getting started, which, if you're the one paying for the car, is genuinely good news either way.